Now let's move from the sky to the bay. Captain John Smith published the first detailed map of the Chesapeake region in 1612, and that map serves as the inspiration and framework for the mission of the Chesapeake Conservancy. They work to ensure a healthy bay for fish, wildlife, and our growing population. To share with us the complex challenges of managing this vast watershed, please welcome Jeff Allenby and Cassandra Pallai.
Thank you, Marcella. To get started, we are going to multitask for the next 7 minutes. I'm going to ask Cass to run a large image processing model while I explain some of the problems and the science behind it. I want to share this with you because it has fundamentally changed the way that we think about remote sensing and the way that information can allow us to guide meaningful action in the world around us. We'll come back to this in a few minutes. We are a small organization dedicated to protecting the Chesapeake's history, culture, and natural resources. But trying to help manage a 3,000-mile water trail across 6 states in the District of Columbia in a 64,000-square-mile watershed is no easy task. So we have turned to technology as a way to help focus our efforts. We partner with state, federal, and nonprofit partners throughout the watershed to help reduce the amount of sediment and nutrients that are entering the Chesapeake's tributaries. Our strategy is to implement precision conservation, getting the right practices in the right places at the right scale. We're figuring out where we need to plant trees along streams, where we have opportunities to improve urban tree canopy, and where we can restore wetlands. Thanks in no small part to many of the people in this room, data like the National Land Cover Database is allowing us to do extensive modeling to identify the watersheds where these actions would be most effective. And the watershed states are taking this information, and they're identifying and directing the conservation efforts and restoration efforts to the sub-watersheds, where we have the greatest improvements in water quality to make. But as we zoom in, we can start to see that the NLCD becomes pixelated, just as we get to the level that local planners need. This has led to confusion and sometimes even tension between regional planners and local jurisdictions. The data that's being used to set pollution limits just isn't specific enough to be able to direct on-the-ground implementation. There was a need for a consistent data that captured the complexity and the detail of the landscape and covered the entire Chesapeake Bay watershed. So we did what society has done for centuries when faced with the seemingly insurmountable task of deciding where to work and what to do. We used the latest tools to create a better map. In December, after a lot of hard work by a dedicated team of partners, we released a 1-meter land cover data set for the Chesapeake Bay watershed, free for anybody to download and incorporate into their management efforts. With 900 times the amount of data as the NLCD and over 90% accuracy, this information has the detail to see individual trees, driveways, and all of the other features that were just being missed by that 30-meter data. But it's not just for a small project area or just for a county. It covers over 100,000 square miles in the 206 counties that make up the Chesapeake Bay watershed. Now, while this achievement was great, we immediately started to think about the future. Because while it's important to know what's on the ground, what's really valuable is knowing what has changed since the last time that you mapped it. We were challenged to think about ways that we could reduce the cost and the time that it takes to produce this data by leveraging new advances in distributed processing and cloud computing. We also needed to find a way to remove LiDAR from our classification workflow because we wanted to expand this data beyond the data-rich Chesapeake. Let's look at how we accomplished this. We were able to overcome the limitation of using just 4-band NAPE imagery by creating an image processing workflow that segments our images based on a combination of 3 computed bands: a vegetation index that compares the near-infrared to the red and blue bands, a brightness calculation that looks at the pixel values, and the chromaticity of the near-infrared band, which looks at the quality of the color. While each of these layers may not provide you all of the information that they need by themselves, we can combine the 3 bands in a raster function to create a new false color image. And this may look strange to us, and it does to me, but this is exactly what the computer needs to be able to draw boundaries between similar-looking features. We can clearly see the differences between situations that have traditionally caused a lot of trouble for us, like this road corridor going through a shadow. And to help us see these edges even better, we can turn on a dynamic raster function to preview our segment boundaries. This layer can help us understand how the computer is seeing differences in the image, as well as where it is grouping similar pixels together. We want to find a balance between creating these clean edges between features without creating millions of tiny segments. For our updated land cover, we are going to create 5 initial classes: barren land, impervious surfaces, low vegetation, trees, and water. Over the course of a few hours, we used our segmented image to select training sites for each of these classes, and then used a random trees classifier to be able to do our classification. Once we have our classification definitions, we can combine each of our individual functions into one larger chain and run our entire classification at once. But we need to figure out how we scale this approach to an entire county, state, or even the entire Chesapeake Bay watershed while creating persistent data. Luckily, we can apply our raster function to an image service hosted in Microsoft's Azure cloud. This allows us to process the data tremendously quickly, even though it's a bunch of it. And in case you haven't realized it, this is what we started at the beginning of our process. Just to give some context for the scale of what we are doing, it took us 18 months to process our previous high-resolution land cover data set. A lot of this time was spent waiting for the over 20 terabytes of imagery and LiDAR data to process through our local machines. But distributed computing is removing processing as a barrier, allowing our staff to focus more time on selecting great training sites and improving the data after the fact. We can see that our results look very similar to what we saw dynamically drawing for a sample area. But in this case, we processed data for the entirety of Kent County and Delaware. This job ran on a 10-machine cluster in Microsoft Azure, each with 20 cores, and covers 53 USGS quarter quads of imagery, or about 3.8 billion pixels. And it ran in under 5 minutes. If we were to have done this locally, it would have taken us over a week. And it looks fantastic, not just where our training sites were, but at the other end of the county. What we just applied to Kent could be applied to any county throughout the Chesapeake Bay watershed, or really any county that we have NAPE imagery, which is the entire country. And while it was designed to work on NAPE imagery, there's no reason that this process, this workflow, couldn't be applied to whatever imagery data sets that you do have. But as a wise man once told me, Jeff, this data looks great, but how is this going to change how we work? To explain a little bit about how we're using this information in our daily work, I'm going to pass it over to my geospatial program manager, Cassandra Pallai.
Thanks, Jeff. While it's exciting to remote sensors on its own, raw land cover data needs analyzing in context with many different data sets to provide information useful to managers. One example and a major strategy for reducing pollution inputs into the Chesapeake Bay is planting trees along streams and rivers. To that end, by 2025, Pennsylvania aims to install 95,000 acres of riparian forest buffers. Yes, this is an enormous task. It's the same as planting all of Washington, D.C. 2.5 times over with 20 million trees. Planning for this enormous task demands cheap and efficient methods that will both identify and prioritize planting opportunities across the state. The Chesapeake Conservancy is working with Pennsylvania government agencies and local stakeholders to answer this call. The workflow for identifying riparian buffer gaps uses a simple overlay analysis. It's a set of steps that many of you have run on your own data, but with raster analytics, we can do it much faster. We evaluate the land cover data, a LiDAR-derived water network that the Conservancy has produced for the Susquehanna River watershed, and a 35-foot wide Euclidean distance from streams layer that indicates the width of our riparian buffers. Since we want land that is not trees, shrubs, or wetlands, we will evaluate that within the riparian buffer gap to identify the planting opportunities. This model we've turned into a raster function that will run on image services, which have been published to Microsoft Azure. Because of distributed computing, we can quickly identify riparian buffer gaps, not just in this subwatershed, but across the Susquehanna. These are potential places to send our field crews. So, following these steps, we processed the 48 billion pixels that comprise the West Branch of the Susquehanna in just under 12 minutes. Run as a desktop analysis, this step by itself would have taken 20 times as long. This time savings is incredibly valuable. Many of us understand the tight deadlines associated with working on grants or contracts. Extended processing hours often occupy weeks or months that could be spent analyzing results for more information. Here, raster analytics has bought us time to think about prioritizing where to send our field crews. Priorities change depending on the organization and where they are doing plantings. With this type of workflow, we can get timely, actionable information that can guide our actions on the ground. We're not building the map anymore. We're working with a new dynamic model that can react to real-world situations. Each of us can have and update our own custom map that will guide our actions on the ground. Today, we've harnessed the power of distributed computing for our organization to operationalize precision conservation across the Chesapeake Bay watershed and beyond, to put the right trees in the right gaps in the right watersheds. Thank you.
Thank you. Thank you, Cassandra. Thank you, Jeff. It's exciting to see the work that you guys are doing.